assuming that they have the same cross-sectional area, which one do you think will have more resistance? That's right. Remember the demonstration I showed you guys? To improve the structure from buckling, you have to resist what? Moment. Agree or disagree? You have to what? Resist moment. Okay? So point A, on the top structure, A is P, B is P. How about the bottom one? Let's look at point B. Okay, point B is very straightforward. What do you think point B is? Yes. Or we call it what? Built in. Right? So when it's built in, if I remove A, how will the structure look like? It will still stand vertically. The one at the top, when I remove A, it will what? Topple. And this is because point B, the moment is not equal to what? Okay, you get that? Yes? Now focus on point A now. Point A can go what? Up and down. But it is also what? Empty. So it also has a what? Moment. It can resist what? Moment. Are we clear? So for this case, we have a case where the top and bottom, so we call it fixed at the top, and we also call this fixed at the bottom. And then if we write down our boundary condition, so when we have x is equal to 0, right? We also know y is equal to 0. For this case, m is not equal to what? 0. Okay. And at the top, x is equal to, or at the bottom, x is equal to L0 or L, y is equal to 0. And we also know that moment is not equal to 0. Now, whether it is thin or fixed, it is dependent on the what? Moment. And for this case, LE is equal to 0.5 L. So the E deformation is important to see the deformation deformation pattern. So the deformation pattern now looks like this. Don't look and see nothing, yeah? Follow the way I draw it. Follow the way I draw it. Okay? So how do I draw? I draw that at point A is close to what? Vertical. Then it has a convex or concave structure or looking, and then at point B is against what? Against vertical. That's a steel roof. That's my friend with the steel roof. This place is like a church. You don't move. They move about, mingle around, you might get lucky. Are we clear? Right? Don't just sit beside your friend, get to know one another, okay? Drink some beer together. Yeah, no, it's okay, it's okay. I'll think with you, man. So, why I do it vertically, I have 3 more pens. Okay, so yeah. You need out to pass this course. Right? So You can see over here, right? If I were to bend this, you can see the structure over here. This is the what? Bend here. Okay. Okay. So, how you be more discreet? Thank you so much. Okay. So you can see when LE is equal to 0.5, what does it mean? It's more. So that's where what you can see, the buckling is not also dependent on the what? Oh, I'm getting lightheaded. You can see it's not just dependent on the what? On the length, not just dependent on the cross-sectional area, but dependent on how your structure is what? Now, be clear. That is more important than anything. So 3 factors that will affect buckling resistance. So 1 is the length. 2 is the cross-sectional geometry. And number 3 is how the structure is held. Okay, how the structure is held. These are the 3 things that are very important. Okay, now let's look at, so now we have come up with the equation. Some of you will say, Eugene, so what? Yes or no? Okay, so what? So now the next thing that we're going to do, okay, I don't think we have time for this example. Next week we will do this example, okay? So now let's focus on the critical stress is equal to pi squared E over L over R squared, okay? So now we are going to try on example number 1. Okay. Now, given that the stress allowable is equal to 250 times 10 to the power 6 Pascal, and we have a Young's modulus of 200 times 10 to the power 9 Pascal. So from here, we can calculate the L over, so we're going to determine the L over R ratio. Okay, the L over R ratio. So the L over R ratio will be equal to pi squared E over stress critical. And then the whole thing is equal to square root. Okay. Ooh, yellow people can't take alcohol really well. Like me, okay, I'm gone, okay? I could lie down and sleep now, okay? It's normal. We don't, genetically, we don't have that enzyme to get rid of the alcohol. I'm as red as a lobster now. Moral of the story is Eugene is a cheap drinker. Invite him for weddings, you get big present, and you don't need to spend too much on him. This is equal. So now when we do that, so you have so it's 88.857.
So what does this number actually means in real life? Okay, what does this number actually mean in real life? So now our draw on our x-axis is the L/R ratio. And on the y is our stress allowable. And at a certain point over here, this is equal to 88.857. Okay. What do you have after this class? Nothing? Oh, you have something. Yes. You can also put in as the allowable is also critical. Means allowable means what? That's the maximum that's allowed, right? Later we will do your factor in boundary. Okay. So for this case, okay, I will say the 20 factor is equal to 1. Okay. So once you put this in, how it looks like. So over here, this is going to be at 250 megapascal. So the structure can withstand 250 megapascal. And then after that, it's like 50, you know. I'm past 50, right? It's like performance of human being, you know. Once the 88.857 is like human being, okay? After 50, nothing is up, everything is down. So for this case, right, on this side, your design criteria is what? Is the critical stress is equal to P over A. Okay. After you pass 88.857, you have to consider buckling design criteria. Where you have your stress allowable will be equal to pi squared E L over R squared. So on the right-hand side, sorry, on your left-hand side, if your L over R is less than 88.857, right? You don't need to consider what? Okay. On the right-hand side, when your L over R ratio, right, is greater than 88.857, you cannot just do the normal stress analysis. You have to do what? I believe we have seen a structure like this before. Okay. And I want you to talk to me. Okay. If we now have a structure and the structure looks like this. You've seen this problem before, yes or no? This is point A, this is point B, and this is point C. And then at point B, we have a load BY.
BC, if you look at this structure, member BC is under compression, and member what? AB is under what? Tensile. So you only do buckling in what? Member BC. Now, if we were to take the whole thing again, now, what will happen if we were to push this up? Which one do you have to do buckling? Yeah. You have to do buckling on AB because now this is under what? Wait. This is under compression, and this is under what? Tensile. Are we clear? So this is just a very brief example. Later on next week, we will focus at the joint. What if the structure is under single shear configuration? What if the structure is double shear configuration? Enjoy your weekend. Be safe, okay? And don't be naughty.